Day 7, I'm going to be talking about binary trees. Well, and trees in general. So I want to start by just recalling the definition of binary trees back from day 4 structures, where we mentioned them as another structure that you could care about, but didn't really go into much more detail. So we're going to spend today and some of tomorrow talking about these trees in a little bit more detail. And then back on day 10, we'll define yet another kind of tree that'll be really fun. So let's start with just this generic notion of binary tree. I've got the data type from day 4 up here. Right here's the definition. A binary tree is either empty or it's a node where a node holds a value of some type x. Trees are homogeneous, just like our lists were homogeneous. So you'll only hold values of some given type in a given tree. Right? It'll be all nats, all bools, or all bases, or all lists of nats, or whatever. Right? It'll be uniform. And it has two children, a left child and a right child. Right? And we drew these diagrams where you would have the node at the top and then the children coming down on each side. Okay. So the parameterized type, we do the implicit arguments thing and so on. So we're able to simply say like, oh, what's the type of empty? Well, empty is one of these things where, okay, Cox's going to guess the type X, so it gives us this funny notation. If we're explicit, then okay, empty at nat is the empty binary tree that would hold nats. Okay, here's a binary tree that holds bools. This is a leaf node, if you recall our terminology, because both of the children of this node are empty. Here's another leaf. Turn over a new one, this time a nat leaf, where it's just the leaf 5. Okay, this one isn't a leaf node. This is a tree where we have G at the root, and then it has one child on the right that is a leaf containing just C. And then if I recall correctly, this was another example I think we gave then. If not, we have it now. Where this is a more complicated tree. 25 is the root. Here's the left child. Here's the right child. Itself a complex tree, right? Something like that, right? And then we had you define some functions, so you'll get things like size. So we don't have that defined in the file I'm lecturing from right now, but this would return the number of sort of actual nodes you get here. So I would expect size on this to be 4. We can define, we define functions like isLeaf. Here's a function root. So isLeaf in the homework, I think, accidentally had the fixed point keyword. Sorry about the misleading hint there. Here's a function root that tries to get the root out of a tree. Say, oh, give me the root out of this big complex tree, and it'll find you the root value. Or we can define a function to make leaves for us. This just saves some writing, right? So like here, this tree right here, this tree is exactly the same as this tree, the actual tree. That tree is the same as that tree. This is what I would call a smart constructor, right? It's just like, it's a way of, like leaf we're pretending is like a constructor. It's a function we wrote that constructs these binary trees, and it just says, hey, I know the shape that I want. I want it to look like this. Just do the pattern, do the thing. Okay. That's just a little bit of sort of recall I wanted to do. If this doesn't make total sense, maybe go back and watch the videos from day 4 where I go into more detail about, okay, how do you draw these? How do they work? What's really going on here? Later on, we're going to look at some other kinds of trees, and then we're going to write a bunch of functions that work on various kinds of these trees. Okay, talk to you soon.